Today, we will be learning about DC machines, specifically DC motors. My name is Jon Patrick Valdez. I am currently a third year electrical engineering student of Bicol University. This was made in accordance to my subject Electrical Machines 1. So, we were given two problems regarding DC motors. Before we can answer these problems, we first need to understand the basic principles of DC motors, the DC motor formula, and then we can now answer and solve the two DC motor problems. So intrinsically, DC motor works in the same way as a generator. So theoretically, a motor and the generator can be used inversely or can be used both a motor and a generator. Okay, with that in mind, an electric motor is a machine which converts electrical energy into mechanical energy. Same rule applies as the generator, but in an inverse manner. So what does it mean? Basically, just meant that their output and input switches or inverses, resulting with a swap or changing of the current direction, resulting, of course, with different formulas and results. That's the main point the most basic difference of the motor and the generator. Remembering the concept of the magnetic circuits, we will remember that the force magnitude is equal to the magnetic flux times the current times the length of the conductor, with the magnetic flux perpendicular to the axis of the conductor. Now, what this formula gives is only the magnitude. Thus, in DC motors and DC generators, it is important for us to know the direction of these parameters for us to know how it will work or what will the mechanical output be. Thus, we have the Fleming's hand rule. It gives the direction of the current, motion or force, and magnetic field through the use of the left and right hand. Note, when using the left and right hand rule, it is important to know its purpose. The Fleming's right hand rule is for the generators, while the Fleming's left hand rule is for the motors, where the current differs, as in the right hand rule it is the induced current, and the Fleming's left hand rule is the current, and the torque follows the rotation, or it follows the torque's rotation. So in this figure, we can see the circuit of a motor. Note that it is almost similar, as we can see, it is almost similar to the generator. It only differs, of course, to the voltage supply as well as the direction of the current. With that, we can now use the two basic laws, which is the Kirchhoff voltage law and the Kirchhoff's current law. Applying the Kirchhoff's voltage law in the loop from positive to negative, where EB will be from the point of intersection of EB and the other side, we can have V minus EB minus IARA equals 0. Because, as we all know, the sum of voltages will always equal to 0. in a closed loop. Now, applying Kirchhoff's current law to the node where the positive side intersects the shunt field, intersects with the armature, we can determine I equals IA plus ISH, where IA is the current armature and the ISH is the current shunt or the shunt current. Finding IA, we have IA equals I minus ISH, where I came from the voltage supply or the current of the voltage of the supply. Therefore, combining the two formulas, we get the Buck EMF equation, which is equal to EB equals V minus I minus ISH multiplied by RA. And of course, since we are dealing with motors, we will have torque. But first of all, what is torque? Oh, I think we all have heard it in our physics class. And also we had applied it in our statics classes. So, remembering those ideas and lessons, we have torque is the moment axis. It is the twisting of a force about an axis, given its force is direction, giving its force direction perpendicular about the radius or the line from the center. So we were given a formula that power is equals to T times angular velocity, where n is of course RPM. So 2 pi n. 2 pi n alone represents RPS. Converting it to RPM, we divide it by 60. Isolating T, we will now have the torque formula, where C 60 over 2 pi n times P. Note, there are made two types of torque, at least in our module. There is the shaft torque and there is the armature torque. So this type of torques depends upon the output power or the power out or even out power. Now that we have studied the needed lessons and formulas for these problems, we can now start in solving the two problems given to us. So, problem 1. A DC shunt machine has armature and field resistances of 0.025 ohms and 80 ohms respectively when connected to a constant 400-volt bus bars and driven as a generator at 450 rpm. It delivers 120 kilowatt. Calculate its speed when running as a motor and absorbing 120 kilowatt from the same bus bars. And the second part of this problem, deduce the direction of rotation of this machine when it's as a motor, assuming a clockwise rotation as a generator. So first, we need to fix the figure, or we need to write the figure first so we can understand it better. So we have two types of circuits, the generator circuit and the motor circuit. Seeing that, we can now form the relationship between the two. So first, we need to find the motor speed or the speed of the machine acting as a motor. So given R shunt is equals to 80 ohms, the combined resistances of the series of the field and the armature is equals to 0.025 ohms. The speed of the generator is 450 rpm. The P absorbed or the power absorbed and the power delivered is 120 kilowatt and the voltage is 400 volts. Knowing that, this is our solution. We know that we know that they have the same parameters, and we know that we can assume that they have the same type of configuration of the circuit. So, using that assumptions, we can use proportionality and ratio and proportions. So, we know that the formula E is equal to PNZ phi over 68. But since we assume that the other parameters are constant, we can replace the P and PZ phi all over 60A as K. They will all be treated as constant. Doing so, we will have the equation E equals Kn. Of course, this as the constant, we can now use it as E over N. Note that E equals P and Z phi over 60A is similar to the back EMF and the EG or the generator voltage. Now, we can equate the two. Since K is equals to E over N, where EB over NB equals EG over NG equals K, we can now determine the following relationship: NB over EV equals NG over EG. So instead of doing it one by one, we can actually solve it and using direct substitution. Isolating NB, it will now equate to the speed of the generator multiplied to the EB, which is actually equal to V minus I minus ISH times RA. Its totality multiplied to the speed of the generator all over the EG over or EG or V plus I plus ISH over times 0.1, or actually it's just the armature or the RA, or it's actually 0.025. It's a typo. It's 0.025. Upon knowing that, directly substitute the values. We have NB equals of 450 and so on, resulting to the answer 433.4 RPM. And that value is almost close, or it's approximately similar to 435 RPM, which is the answer of the module. Now, in the second part of the problem, we can now use Fleming's hand rule. Remember that in Fleming's hand rule, we use the right hand for the generator and the left hand for the motor. It is given in the problem that in the generator, the rotation is in the clockwise motion. So we need to change our thumb into the clockwise rotation. So there, in my end, it's clockwise. Thus, we now determined that this is the current's direction. Knowing the direction of the current, we will now use the direction of the current in our left hand. Also remembering that in the left hand, it determines the direction of the motor because the motor uses the left hand rule. Knowing this, we have concluded that the rotation, when they are at the same direction of current, it opposes each other. So if a DC generator was turned into a DC motor, then if it were to rotate, it rotates opposite to the generator. Remembering that the generator rotates on a clockwise motion, then the DC generator or the DC motor will rotate in the counterclockwise direction, thus having our answer as counterclockwise. Now, we go to the second problem. A 20 kilowatt DC shunt generator delivering rated output at 1000 RPM has a terminal voltage of 500 volts. The armature resistance is zero point 0.1 ohms. The voltage drop per brush is 1 volt and the field resistance is 500 ohms. Calculate the speed at which the machine will run as a motor taking an input 20 kilowatt from a 500 volt DC. As we can see, the problem is almost or pretty similar to the first problem. And this problem actually helped us understand the difference between the motor and the generator. Now, applying what we had learned, we can see that truly the current affect the output or the switching of the outputs affected the values of the or the parameters. Okay, so we now use the figure. The first figure is a motor, the second figure is a generator, similar as the before. But now we will be finding the motor speed given a voltage drop. In this case, instead of using the normal form, the usual formula that we are used to, which is V minus EB minus IARA, we then apply again the Kirchhoff's voltage law. We now have V minus EB minus IARA minus voltage drop. Okay, so here's the given. RSH is equal to 500 ohms. RA is equal to zero point 0.1 ohms. The speed of the generator is 1000 RPM. The P absorbed and the P released is 20 kilowatt and the voltage is 500 volts. The voltage drop given was 1 volt per brush. We have two brushes in an armature, therefore we add the two or multiply it by 1, we now get 2 volts. Assuming that their configuration are the same, we now have the constant PZ phi over 60A. We can treat it as the proportionality constant. We now have E equals Kn, which is K equals E over N. Same principle as the old problem or the problem before. We now have EB over NB equals EG over NG. Since we are finding for the speed, we now need to apply reciprocal the formula. We now get NB over EV equals NG over EG, where NG is the speed of the generator and NB is the speed of the back of the motor. Isolating the speed of the motor, we now get NG times EB over EG. Substituting the formula through the use of which we applied the Kirchhoff's voltage law, we now have Ng times V minus I minus ISH times RA minus V drop all over V plus ISH times zero point 0.1 plus V drop. Now through direct substitution, we now have the value of 1000 oh so forth, having and figuring out that the answer is actually the speed of the motor is 976.29 RPM. In the module, the answer was 976.1 RPM. But this answer is pretty close and it's approximately similar. And we follow the formula, so hopefully I think it's correct. Thank you for watching the presentation and I hope we learned something new today. Again, my name is Jon Patrick Valdez and thank you for watching.